Hello and welcome back to this course on FEM for CFD and Multiphysics. So now we are at the second talk and we are actually going to start off with some theory. So let's start off by talking a bit about differential equations. So differential equations can be thought of as the language of change. From a contribution standpoint, we could also think of them as modern day oracles. Because in the past, we used to go to oracles or soothsayers who would look at the wind and the stars and give some nice predictions. That's because this is a very turbulent world, always changing, very dynamic. So we really want predictions. So now instead of oracles, we just go to differential equations, right? That's because we know that if we want to study some problem, we can use mathematics to construct a mathematical model. And if this model is really representative of what's happening, and if we seek a solution in a correct way, then we are able to get some really good predictions. The problem is really that while we can write this model using a piece of paper and a pen, we cannot solve it that way. So that is because the real world applications, the geometries on which these differential equations and these mathematical models are working, that geometry is complicated, and the differential equations are also complicated. There is also multiphysics where they are getting coupled. There are problems like turbulence which we cannot solve analytically. So that is why we need numerical methods, and that is where the computer aided engineering tools come in. So let's motivate this idea a bit more by looking at the very simple the simple definition of the derivative which we learnt in the very basic undergraduate calculus course. So let's consider these 2 points, and they are separated by a small value h. Okay, and there is this smooth function defined over these 2 points, a function u. Now let's say I want to approximate the first derivative u dash of x on this basically geometry. So this is the definition which we learned, right? And this definition tells us that as h becomes a smaller and smaller number, this expression, which is basically just an algebraic expression, that becomes a closer and closer representation of u dash of x, right? So which means that if these points are coming close to each other, I can find out the derivative at this point simply using an algebraic relation. And that also means that if I have differential equations which have this u dash of x, I can now use algebraic approximations for that. So this leads me to the concept of discretization. So let's say I have this geometry. I want to solve some complicated differential equation which I cannot find an analytical solution. So I just break this geometry into smaller and smaller parts. So let's say I put a large number of nodes onto this geometry. The more number of nodes I put in, the smaller the distance between those nodes, the better and better approximation I have. So that is basically your that leads you to the concept of discretization error. So as you make these points closer and closer, so your discretization error is becoming less and less. That means your algebraic equations are becoming more and more representative of the actual differential equations, right? So there are many methods to do this. You don't actually have to construct a mesh. Typically in computer aided engineering softwares, you design a geometry by using CAD, and then you use a meshing software. That's the most common approach, because the most common approach follows creating a mesh. But there are also meshless methods like spectral methods, but they are more niche. Finite elements can be used in a meshless way, coupled with meshless methods, but primarily it is using a meshed approach. Okay, so here in this course we are only going to think of a meshed approach. So let's look at what a mesh is. So I have shown 2 representations here. The left hand side is what is called as a structured mesh, and this is pretty simple to understand. This is a square domain, square geometry, in which you are just putting in a lot of squares. Naturally, this can only be used for very overly simplified geometries. In most of the cases in the real world, we are following this kind of an approach, which is an unstructured approach. So here you can see that the discretizations can be stretched or pulled or compressed a bit. This is subject to some rules, and that is why we have meshing softwares to do this. But this is the approach which is commonly used because you can fit really complex geometries by using this kind of an approach. And finite elements are really good at using this kind of an approach and even seeking higher order solutions on this kind of an approach. Okay. So we want to move towards finite elements. We want to understand finite elements, but there are a lot of concepts. It's better to tackle those concepts using FDM and FEM first, because these concepts are really the same, and FDM is quite simple. So let's approach those concepts first from an FDM standpoint. Then we'll look at some conservation laws or piecewise continuity, those kind of concepts in FEM, and then finally we'll go to FEM. Okay. So what are finite differences? So this is a method by which we are again seeking the solutions for differential equations. Here we represent or rather approximate the derivatives by difference quotients. We place them on discrete grid points, and then we solve these algebraic relations on discrete grid points to get the solution of our differential equations. So probably the most important relation in finite differences is the Taylor series approximation. So here let's consider these 2 points and this smooth function again. So my objective is to understand how u of x plus h behaves with respect to u of x. So the Taylor series allows me to express u of x plus h in terms of the derivatives of u of x. Okay, and this is an infinite series. And you can see first is the 0th order derivative, then the first order derivative, then the second order derivative, and so on. And these are scaled with powers of h. So in discretization, h is a small number. So if this is 0.1, h is 0.1, then this term is scaled with 0.1, this term is scaled with 0.01, and so on. So these terms start becoming smaller and smaller as you go ahead in the expression. And this allows us to make approximations, because then we can say that we can just ignore some of these terms. Okay, so let's do that approximation. Let's just divide every this Taylor series throughout by h, and let's just rearrange it. Okay, very simple. Now construct an approximation by saying that since h is a small h is a small number, we'll just ignore this, the red part, and we'll only consider this green part. So this approximation is called as a forward difference quotient. So let's look at what this is doing. So we know that a geometric representation of u dash of x, the first derivative, can be thought of as the slope or the tangent. So let's take a tangent at x, right? So if I just extend it, so if let's say that u of x is known to me for this case, and so I take a tangent at u of x, I extend it to x plus h to get this approximation. So you can see that there is a big error between these two values. And so there is a big error in this approximation. But if I made h smaller, so I can see that the error really reduces. So this is the phenomenon which is called as convergence. So as h becomes smaller and smaller, the approximate value starts approaching the true value. This is the process of convergence, and there is a rate at which this occurs. So this rate is determined by these red terms, and the largest contribution to the red term is from this term, which is the largest of them. So this is scaled with h, and thus we say that this approximation will converge at the rate of order of h. So now let's move towards understanding some problems here. So let's look at the initial value problem first. So this is typically used in the case of time-based differentiation or time-based differential equations. So let's consider this kind of a differential equation: du by dt is equal to f of u. So this is a time derivative. So in an initial value problem, the initial value is known. So let's say we are starting off at time t. So u at time t is known. So I can evaluate f of u at this time, and then I could approximate du by dt by the forward difference. So I take a tangent, and then I get this approximate value at t plus h. I again take a tangent, so this is an approximation of a tangent rather, okay? And we are marching forward in time, okay? We march forward and make these approximations. So you will accumulate error if your discretization is large, okay? So if h is small, then these will be accurate, okay? Another way of looking at, so this is an explicit way. Another way is an implicit way. So here just the difference is that instead of evaluating this function f at t, we evaluate it at t plus h, okay? So we just make a small change, that we evaluate this expression at t plus h. Since this is unknown, so the way to solve this is iteratively by using a guess value. So first you plug in a guess value of u of t plus h. You evaluate a new value of u of t plus h using this equation, solving it. and then that new value becomes your second guess. Plug it in, again calculate a third guess, and you just keep looping this till you reach a convergence. Okay. So this kind of a scheme is numerically stable, but we are not going to look at numerical stability in this course. It's not really required. So this is what is called as the implicit scheme. Generally we talk of this as alpha schemes, okay, alpha family of schemes. Okay, so if I put alpha is equal to 0, so alpha is just used to interpolate f of u at t plus h and f of u. Okay, and you can just derive different schemes. This is the first scheme which we saw, alpha is equal to 0. This is the second scheme which we saw, alpha equal to 1. So I am not really expanding on these different schemes. So our objective is to go towards finite elements. But we should say that really the implicit schemes are used when you want to deal with larger time steps, and explicit ones are used for smaller time steps. But this is mainly due to numerical stability rather than the accuracy. Okay, I mean the order of h accuracy. So now let's move ahead to boundary value problems. So in boundary value problems, the values at the boundaries of the domains are specified, and our objective is to find out the internal values. So you could think of a steady state problem as a good representation. So du by dx is equal to f of u. This is my steady state problem. The values of u at x and x plus 3h are known. My objective is to find out the values at x plus h and x plus 2h. So I could simply write down these two boundary values as two expressions in blue, and I could approximate the u at these two values by writing these kind of equations using the forward difference. So here I am constructing two approximations of tangents, and then I am using a simultaneous solution. Okay, so if I put in more number of grid points, so I would be putting in a lot of tangents here, okay, and then I would just be solving them simultaneously. So if I put in a lot of points, so this curve can be represented by a lot of straight lines, right? So that's the idea. So I would converge if I use more number of points. So now let's actually solve a diffusion problem. So this will become much more clearer. So we'll look at a diffusion problem because diffusion is more representative of what's happening in the real world. So this is your diffusion equation. We'll derive this, but right now let's just simplify this to this expression. Okay. Now this is a second order differential. So let's try to understand a bit about second order differential and how to construct an approximation for that. So if a first order differential can be thought of as the slope, the second order differential can be thought of as a curvature. That's because a line has zero curvature. A second derivative of a line is 0. So anything which has a finite curvature, you could think of it minimally as a quadratic approximation. That is something which has an x square term, so which is also called as a parabola, or cubic or higher order term. Okay. So minimally we need 3 points to represent a parabola, because 2 points at best gives us a straight line fit. So here if we need to approximate curvature, we will need 3 points. So let's consider x minus h as another point. We'll expand the Taylor series around these 2 points, x plus h and x minus h. And since we are using minus h here, the odd order terms are getting negative. Okay, so adding both of them will cause these terms to drop out, and I'll get this nice expression for the second order derivative. And this is the leading order term of the red part, which is your error, which we are ignoring. And this is order of h square. That is because you are using 3 points, so it is more accurate. Okay, so this is like fitting a parabola again. So let's now go ahead and solve quickly a very simple problem. So let's consider this length. So this 1D domain running from 0 to 1. Okay, the values at the boundaries at x equal to 0 and x equal to 1 are specified. So my problem is just to find out the value of u at x2 and x3. This is my differential equation. So I can simply write the first and fourth equation easily, and the second equation is basically represented by using the second order difference approximation. Okay. So I have just written down these two equations, and you can note that there are 3 variables here. So even if I were to add in 10 or 100 equations, they would again have just 3 variables. Okay. So I could write this into a matrix form. Okay, and then I could just simply invert this matrix, solve it. Naturally, the analytical solution which I am showing here is equation of a straight line, because the differential equation is just curvature is equal to 0. So this is u is equal to 1 minus x, and you can see that these 2 points lie on u is equal to 1 minus x. Very simple. Now if I were to put in more points, I would get this kind of a matrix. I have just 3 unknowns on every row, on every equation. So I would get this band, okay, which is also called as a tri-diagonal matrix. So there is a so the diagonal really has 3 variables. Okay, every row will have 3 variables. So rest are all 0. Okay, so this is what is also called as a sparse matrix, and you have special linear algebra libraries used for solving these kind of matrices. And these are common for local approximations, because for local approximations all of you get a lot of zeros here. Okay, if you make a global approximation like in spectral methods, so all of this will fill up and you will get a dense matrix. And so for that you have different kind of solvers which are dense matrix solvers. But we can also choose to make this matrix denser by adding more number of variables. Okay, so if instead of 3 variables, if I just extend this idea, so if instead of fitting a parabola, I take instead of 3 points, I take 5 points. So I would get a pentadiagonal matrix, which is a better approximation, because now I am capturing the curvature using 5 points. Okay, so that is basically the idea of higher order approximations in your finite differences. Okay, so you are not actually going to a global scale, but you are just increasing the band. Okay, the band size. So let's look at this a bit geometrically. So for the second order approximation, you are just fitting parabolas instead of straight lines, and you can see that these parabolas are overlapped. So if I were to instead of 3 points, I were to use 5 points, you can think of a quartic expression, and that is 4th order more accurate, and the overlap is also more. So you can understand that the solution or rather the equations are really enmeshed together in a much better way, and so the simultaneous solution is also much better, right? So now let's move a bit ahead, and let's look at higher order approximation for the first order derivative also. Let's show that this can also be done. We'll not go beyond this, but let's just motivate this idea. So for doing the higher order approximation for the first derivative, the idea is that fit a parabola and then take a tangent to this parabola. Okay, instead of just using 2 points, use 3 points. So again we expand these Taylor series, and now instead of adding, we subtract them, so the even order terms will cancel out, and I can again get this kind of an expression which has an error which is order of h square. So you could consider you could construct higher order approximation for the second derivative, for any kind of derivative. Typically, so basically the idea is to use the Taylor series and construct higher and higher order approximations and get better and better accuracy. This is a very fast way of solving the differential equations, and really the limitation is that you are using a Taylor series which is using a Cartesian coordinate. So when you go to a 2D geometry, you are basically restricted to x and y Taylor series, and that is why if you have a complicated geometry which has probably a curved shape, so it's very difficult to do this. So finite differences is basically stuck in you just have to use a structured grid approach. So that's really the problem with finite differences, and that's why typically we use finite volumes or finite elements for actually solving real world problems. But it's good for learning purpose, and so now let's learn about errors by using finite differences. So typically we are interested in what is called as the L1 or L2 errors. You could also call them as the L1 error norm or the L2 error norm. So the L1 error is defined as the difference between the simulated and true values and the integral of that. Okay, so here we are using discrete values, so we'll have to use the summation. If my u simulated minus u true is order of h square for my central difference approximation, so I can just solve this and I would get order of h square. L2 error uses the difference of these two values squared and integrated, and then you take a square root of that again. Okay, a bit like RMS approach, though not exactly that. Again, we can use a summation approach to evaluate it for our case. So these are two different kinds of errors, and they are used for different kinds of numerical analysis. So here what we are interested in is the convergence plot. So we want to understand the rate at which the convergence phenomenon occurs. So we can simply do this log plot of log of the step size versus the log of error, and I can get this nice slope which is scaled by the order which I have here. Okay, so let's look at a real world example. So this is a CFD case in which the velocity error is converging at order of 3 and pressure error is converging at order of 2. So you will find this kind of convergence plots in the research papers or for all new different methods. Okay, and these are really important. If I were to extend this line ahead for higher values of h, I would get this value slightly higher, because the other higher order terms in the Taylor series become important. As h becomes smaller, they drop out basically, and so you will see convergence towards the leading order term. And if I just keep extending this, it will eventually just reach the machine tolerance where this will just flatten out. Okay. So this is what I wanted to talk about in the finite differences. Hopefully we have motivated a lot of schemes and a lot of new ideas here, and this will really allow us to make quick progress towards finite elements. So in the next lecture we'll look at finite volumes, and we'll solve the diffusion problem for finite volumes. So I thank you for your attention, and I'll see you again.